Good afternoon, everybody. This is the last podcast in chapter 15, and hopefully you're getting excited. We shouldn't have too many more podcasts left to go. We are entering one of our last chapters and then a few tidbits here and there, so we're getting close to the end of the year. I hope that's exciting for you. So we're going to talk today about solubility equilibria, meaning solubility equilibrium and the solubility product. So we aren't really going to be changing too many rules of things that we've been doing before, so this should be pretty straightforward for you. We already understand ionic solids. We understand that they can dissolve and completely dissociate in water. This equation should be no surprise to you. You can see you have calcium fluoride. I have one calcium ion. I have two fluoride ions. So we have, of course, another K. We had Ka and Kc and Kp and I don't know, K Cindy maybe, I don't know. But here we have Ksp. So here is our solubility product for S and P, meaning solubility product. And so what we're going to try to do is find what the equilibrium constant is for this expression. That is not going to change. So if I can look up on a chart on page, page 718, you might want to take a look at that. You have all kinds of solubility constants. And so I can still write my equilibrium expression for this. And we talk about an equilibrium expression again, that is going to be my Ksp. And remember, it's always been our product over our reactant. So that's not going to change. So we have our calcium ion, and then we have our fluoride ion. And that's going to be, that's a -1, raised to a 2 second power because of this coefficient in front. And we've been doing that all along over the reactants. But what we need to notice here is that we have our reactants, which are a solid. That should ring a bell to you that we have not included any solids all along in our equilibrium expressions, and that's not going to change here either. So here I'm going to draw a crude little beaker, lovely, and we're going to put some water in here, and you guys should know that if I add my salts, my ionic substance into here, that it is going to dissociate. Well, what is really happening inside of here? You need to think about this, that I have some calcium fluoride in here that's starting to dissociate. I have some calcium ions that have already dissociated, and I'm going to have some fluoride ions that have already dissociated. I would have 2 fluoride ions for every 1 calcium ion. What you need to remember is that there might be some situations where these 3 ions orientate themselves to come back into the solid form. Remember, that's what equilibrium is. Well, this going back to the solid form is not going to change my equilibrium constant. What can change in this situation is my equilibrium position, because we could heat this up, we could cool this down, and that's going to affect the rate of dissolving. We could crush this calcium fluoride up so it's super fine, and that's going to change my equilibrium position, but it's not going to change my Ksp. So I do not need to include my solids in here. Now on page 718, you can find what our solubilities of these different salts are. So if I take a look and find calcium fluoride, the solubility constant for this, of how soluble it is 2.4 times 10 to the -4th. And so this is talking about its Ksp and how soluble it is, but we have 2 different functions here. So this is in moles per liter. This is how soluble it is. So when I plug this in, I can find out what my Ksp is. So we got to keep in mind that, I'm going to use one more color here. We have to keep in mind that the same thing that's been happening. So here in my equation, this is a solid, so I don't really need to worry about this. But we know that this is x, and we know that this is 2x because of how we're changing our expressions at equilibrium. So I would go ahead and I would write that I want to find out what my Ksp is. So I'm going to put my calcium as x. I'm going to put my fluoride as 2x, but I know that is raised to the 2nd power. So then I need to go ahead and I need to substitute this number in here. So my solubility constant is 2.14 times 10 to the -4th, and then it is going to be 2 times this number, 2.14 times 10 to the -4th, and then this value is squared. So I go ahead and I calculate all of this, and I'm going to get what my KSP. So this would be my equilibrium constant for the dissociation of calcium fluoride. And when I do that, I get 4 times 10 to the minus 11th. And again, it is unitless. So this number here is how soluble the calcium fluoride is. This KSP is my equilibrium constant for calcium fluoride. So it goes through and it has all kinds of values for you. You can take a look at that. We're going to do another example problem here in just a second. All right, so if I take a look at these are just some general rules here. Salts being compared produce the same number of ions. Well, that's how I can compare them. And what this means is if I take a look at sodium or silver iodide, I have copper iodide, and I have calcium sulfate. It doesn't matter what I'm looking at. As long as all of these are producing 2 ions. I have 1 silver, I have 1 iodide, so I have 2 ions. I have 1 copper, I have 1 iodide, I have 2 ions again. I have 1 calcium, I have 1 sulfate, I have 2 ions. When this happens, then I can go ahead and I can compare their KSP values. I can say which one is the least soluble or which one is the most soluble. So if it has a very large KSP, it dissolves easily. If it has the smallest KSP, it's not very soluble. And I can only compare these types of substances because they have the same number of ions. Salts being compared produce different number of ions. You cannot use the KSP directly. For instance, in this case, if I have copper sulfide, if I have silver sulfide, and if I have bismuth trisulfide, because bismuth is one of those metalloids, you can see that this has 2 ions, this would have 3 ions, and this would have 5 ions. I can't compare these KSPs. They have different number of ions, and there's too many factors here to take a look at. So where we had real general comparisons, where we have a larger Ka and more acidic it is, here we can't really do that unless we can take a look that the ions are exactly the same. Okay, so then you have one more topic here down at the bottom where it says, let's see, where does it say on mine? Maybe it doesn't say it. On yours, there's the bell. It talks about the common ion effect and pH and solubility. So I will come back to that. You won't know that when I do, but I will in just a few minutes. Okay, you probably heard the bell ring, so I'm going to continue here just to finish up this last little section for you. And on your notes, and for some reason on my screen, it doesn't exactly say continue the common ion effect and pH and solubility. So if we take a look at the pH and the solubility, it is going to be affected by adding a salt. So if I go ahead and write another really simple equation so that I can apply this for you, I'm going to take my magnesium hydroxide, and you would recognize that that is not soluble, and so I put a solid there for you. It's going to ionize into magnesium ions plus hydroxide ions, 2 hydroxide ions to be exact. All right, so if I take a look at this, and it's called acidification or basification, and all that means is I'm adding more acid or I'm adding more base to my solution, and what is that actually going to do? So if I think about adding an acid, I'm actually adding that hydrogen ion. So this is acidification, and what's that going to do to the pH? Well, if you think about what's going to happen is if I add this, Le Chatelier's principle is going to say that it's going to shift to the right. And if it's going to shift to the right, then that means if you take a look at this hydrogen ion, what's going to form? Well, you should be thinking to yourself, water. And so what that is going to do is it's going to increase my solubility, because if I have more water in my system, then more of this is going to be able to dissolve. So then by adding this hydrogen ion, I'm actually decreasing my pH because of adding the acid, but my Le Chatelier principle is saying that I'm shifting it to the right and making more water. So I have a decrease in pH here. And so if I'm going to, on the reverse, I'm going to add some more OH, another basic substance that's going to add to my OH. My pH is going to increase. My Le Chatelier's principle says it's going to shift to the left, and so it's going to decrease the solubility of my magnesium hydroxide. I don't have as much water in my system, and so it's going to decrease it, moving it to the left. So as a general rule, if I have a weak acid and a conjugate base, and you guys should know that if I have a weak acid, this conjugate base is going to be strong. And if I have a salt, what's going to happen? That this salt is going to increase its solubility by adding my weak acid. Sorry, I'm spelling that wrong. Solubility in acidic solution. So in general, these salts are going to be more soluble in an acid than they are going to be in a water. And the reason they're more soluble is there's more dissociation here, there's more ions in solution, and it's able to pound away and cause those collisions and cause that dissociation to happen. Okay, so that's basically what I want to talk about here with KSPs. I do want to do one more simple problem, and it's on page 720 in your book, and it's talking about calculating the solubility from KSP. We talked about the big chart that you have in your book on page 718. Well, let's say whatever you have is not on there. And I want to show it to you because it's set up a little bit different in the book than how we've been teaching it to you. And I just want to make sure it makes sense to you. So if we take a look, let's see, sorry, I'm trying to grab a pen here. All right, obviously I have it chosen. So we're going to take copper iodate. Can you guys tell it's the end of the day? And I have a solid substance, and it's going to ionize into copper ions and 2 iodate ions. And again, if I don't know my initial concentrations, they're going to be 0, or I don't know my solubility constant, we should recognize that this is going to be x and this is going to be 2x. Some value has to be given, so in here our KSP is given. And I know that my KSP is equal to 1.4 times 10 to the minus 7th. And if I look at my equation, it would be the copper ions times the concentration of my iodate ions. There's another call over the intercom. And it's going to be squared due to that coefficient out in front. Well, if I go ahead and continue to substitute things in, you should recognize that this is going to be my x, and this is going to be 2x raised to the second power, and that's going to be equal to 1.4 times 10 to the minus 7th. Continue to use my algebra here, and I will see that I have 1.4 times 10 to the minus 7th, and this is going to be 4x cubed. Divide both sides by 4, and you are going to end up taking your cube root of cube root of 3.5, check that calculation, make sure I did that right, times 10 to the negative 8th. And if I take the cube root of both sides, I'm going to see that my x is equal to 3.3 times 10 to the minus 3rd. Now, the solubility of the copper iodate is a concentration, so this is going to be moles per liter, or simply molarity, and that's going to be how soluble my copper iodate is. So you saw in the last example that I gave you that this value was given, and I found my KSP, and here it is not, and I'm trying to go backwards. I just wanted you to see it in both directions. All right, I hope you had a great night, and we are done with these interruptions.